In this quiz, we're looking at the solid state structure, and it's really going to focus on the unit cell. And the first question is asking about why the unit cell, what does it mean to have the unit cell? Do we miss out on things with the unit cell? And this is really just a definition question, but is really, really important to understanding solid state structure as we look at it. The unit cell is the smallest repeatable unit, and so remember that solids are kind of like tile work in a way, where we have a unit that just repeats and repeats and repeats. It has structure, and it's a consistent structure throughout the lattice. And if we look at tile work, for example, maybe it's triangle tiles, maybe it's square tiles, but if you zoom in to a certain small purview, you can see the whole pattern that is really just going to repeat itself over and over. And that's what we have here for solid state chemistry. And the unit cell is the smallest possible unit that contains all of the structural information. And as such, then we don't miss out on any information. And if there's some sort of other structural element that's included that we didn't capture in what we're considering the unit cell, well, we actually just don't have the unit cell yet. We need to define a larger unit cell that's going to capture that information. And as such, the unit cell will contain a different number of atoms depending on the complexity of the structure. Okay, one of the types of unit cell that is very common to look at is called a body-centered cubic unit cell. And here's an image of the body-centered cubic structure that's also included. So the first question is how many atoms are within the body-centered cubic cell? And it's important to know the definitions of the body-centered cubic cell, where we have 8 atoms that are located on the corner of a cubic cell, right? It is, descriptive. It's a cube, and there's an atom on every corner, but there's also an atom that's stuck in the center of the body-centered cubic cell. And with that in mind, we can consider how many atoms are actually there, because what you might notice is that the corner atoms are not completely within this square unit cell, within the cubic unit cell rather. It's also inside of neighboring unit cells. But 1/8 of each corner is in the cell. And if you were to draw these out, what you'll see is that each corner atom is actually occupying 8 unit cells, right? It's kind of like 4 on the bottom, 4 on top. And therefore, for 8 corner atoms that are within this cell, only 1/8 of each is part of this specific cell, and therefore it's only 1 corner atom that's contained in the cell, because each one only has a slice. There is also the body-centered atom, and that one completely belongs to this cell. It's in the center of the cell, and it's completely within this cubic cell definition. So that means that there is 1 body-centered atom that's inside of the cell. This means that there's 2 atoms within the body-centered cubic unit cell, and that's a really important thing to keep in mind for considering anything about density or unit cell volume or anything like that moving forward. Okay. Now let's think about another body-centered cubic unit cell. So this is tungsten. Remember, this is BCC, body-centered cubic, and we'll have that structure we just looked at. And here you're given the information that the unit cell edge length is 3.165 angstroms, and the goal is to calculate the volume of the unit cell in cubic centimeters. Now, one of the things about this solid state chemistry is that a lot of these problems are simply geometry. We've said that the cell has a certain edge length, and all we need to know is the volume of this cell, and then it's a cube. So first, let's translate the edge length into centimeters, because we want to get the cubic volume in terms of centimeters cubed, and we know that the volume of a cubic unit cell is just going to be the length cubed, right? Length times width times height. It's a cube. They're all the same, and so we end up getting this volume in cubic centimeters for the unit cell. All right, with the density 19.3 grams per cubic centimeter, the goal is to calculate the average mass of a single atom of tungsten. And so here we need to rely on the fact that we've already calculated the unit cell volume. The unit cell volume has a volume of 3.17 times 10 to the negative 23 cubic centimeters. And based on this, right, we know the density is a certain number of grams per cubic centimeter. We know the volume that we're looking at. So we can simply use our density formula or conversion to get the mass within this unit cell. And that's going to be 6.12 times 10 to the negative 22 grams. Pretty small amount, but this is on the order of just 2 atoms, right? And that's really important. We have to remember that this unit cell contains 2 atoms. It's 1 corner atom and 1 central atom. And so while we've gotten the mass of the unit cell, if we want the mass of just a single tungsten, well, this is the mass of 2 tungstens. It's 1 unit cell. And so we need to divide that in half, and we get the mass of a single tungsten atom to be 3.06 times 10 to the negative 22 grams. And as a little bonus, if we can get the mass of 1 mole of tungsten atoms, can we assess the quality of how well this calculation has gone, right? It's always good to be able to put things in context. We know that it's tungsten. So if the mass of one atom is 3.06 times 10 to the negative 22 grams, how do we get the mass of 1 mole, right? 3.06 times 10 to the negative 22 grams per atom. Let's multiply this by the number of atoms per mole. We're going to cancel out our atoms and get a unit of grams per mole, 184 grams per mole. And so this is useful, right? Here's the mass of 1 mole of tungsten. It would be 184 grams. Can we compare that to something that we know from the literature? And the answer is yes, right? We go to the periodic table and we get the molar mass of tungsten, 183.84 grams per mole, and that's pretty close. We're limited by 3 significant figures for this calculation due to the density of tungsten only having 3 for the given information, and within significant figures that is in agreement with the molar mass of tungsten from the periodic table.